So, very good evening to all. Uh, in today's lecture, we just discuss some elementary ideas of simple harmonic oscillator or simple harmonic motion. So, simple harmonic, some fundamentals of simple harmonic motion, and some few examples of simple harmonic systems. We will discuss that in today's lecture. So, simple harmonic motion. So, what is a harmonic motion? Okay. So, any motion which repeats itself after regular interval is called a periodic or harmonic motions. Any systems that execute a repeated motion after a regular interval is called as periodic or harmonic motions. Say, for example, motion of planets around the sun. Okay. Very simplest example we can consider is the motion of a planet. Say an Earth is orbiting around the sun. After 365 days, it will retrace its original path, right? So that is called the harmonic motion. So it's a periodic motion. Otherwise, I will call it as a harmonic motion. So oscillatory motion, on the other hand, if it is in case of periodic motion, the body moves back and forth, okay, repeatedly about a fixed position. Then it is called as an oscillatory motion. Okay. In the harmonic motion example, motion of a planet around the sun is just the sun is at the center and the planet, the earth, is revolving around it. Okay. So that is harmonic motion. When we talk about the oscillatory motion, it is a periodic motion, just like in the previous case, with a small difference that the system executes a back and forth oscillation, back and forth motion, or to and fro motion repeatedly about some fixed position. Okay, which means every time after a certain interval, this system will pass through the fixed position and goes to the other end. And once it reaches the extremum of the other end, it will retrace its original path, and again it will pass through the fixed position. So that fixed position is called as the equilibrium position or mean position. Okay. So in such cases, the motion is said to be a oscillatory motion or even vibratory motion. Okay. So the motion of a piston in an engine, motion of a needle in a sewing machine, these are all some examples or few examples of the so-called the oscillatory motion. Okay. In an engine, the piston will repeatedly goes back and move in front and come back. It goes front, move in front and come back, right? It will execute a to and fro motion. So that I call it as a oscillatory motion. When we stitch something using a sewing machine, the needles move back and forth. That is also an example for an oscillatory motion. So the study of oscillation is essential for the understanding of various systems, be it mechanical, acoustical, electrical, or atomic. Okay, whether it is a mechanical, acoustical, or electrical, or atomic. So the oscillatory systems, the studies to understand the various properties of the system is very, very essential. Okay, because this oscillation is executed everywhere. Okay, this oscillation is executed very well, even at the microscopic level to the macroscopic level. Okay, so that's all about the harmonic motion. Now, what is a simple harmonic motion? So there should be a simple difference. There should be some difference between the harmonic motion and simple harmonic. In what way it is different? So if the force acting on the oscillatory body is always in the direction, of the opposite to the displacement of the body from the equilibrium or the mean position, and its magnitude is proportional to the magnitude of the displacement, this body is said to be executing a simple harmonic motion. So to put it in a very simple form, the force acting on an oscillating body is always proportional to the displacement of the body, provided the force and the displacement are always opposite to each other. So such a system is called as simple harmonic. Such system executing such type of motion is called as simple harmonic motion. The simple harmonic motion, or SHM, simply called as SHM, is actually a special case of oscillatory or vibratory motion. Okay, this is just a special case of oscillatory or vibratory motion. Fine. So here I have given some examples of the simple harmonic motion. So this includes motion of a simple pendulum, motion of a simple pendulum, a vibrating tuning fork, a spring mass system. Okay. So you know very well about the simple pendulum. It's a string. One end of the string is fixed to the rigid wall. The other end is fixed. The other end of the string is given a small mass. When you pull this mass and leave it, it will begin to oscillate. Okay. Provided the oscillation, the angle subtended by this mass, by this metal mass, right, should be very, very small. It should tend to zero, but not equal to zero. Then the vibrating tuning fork is a very good example for a vibrational systems or simple harmonic system. Then the other one is the spring mass system. This is also very similar to simple pendulum. Instead of the string we have in the simple pendulum, that was replaced by a spring here. Okay. The rigid wall is there on the top, so that was connected a spring. On the other end of the spring, a small mass was given. You have to pull this mass in the downward direction and just leave it. This mass will begin to oscillate in the to and fro. It will move upward and come backward and move upward and come back and repeat it. Okay. So these are few examples of a simple harmonic motion. Okay. So now let us consider the spring mass system in a horizontal manner. In the previous example, I have shown in the vertical manner, but now we consider it as a horizontal one. So you have a rigid wall here. You have a mass here. One end of the rigid wall is connected to the spring is connected to the rigid wall on one side. The other end of the spring is connected to the small mass M. Assume that this plane is completely frictionless, so that this mass will begin to move smoothly onto the plane. Okay. So F is equals to 0 here. F is equals to 0 here. When the mass is at the rest position, there is no force at all. It is at stationary position. There is no force at all. So now you just pull this mass towards the right and leave it so that this mass will begin to move towards the left. So when you pull this mass towards the right, that you can realize an extension of the spring, and this spring will execute a restoring force that will tend to pull this mass in the backward direction. Okay. So the restoring force always opposite to that of the motion of the object. If the mass is moving towards the right, the restoring force is directed towards the left. Okay. Next, you have a mass here, same one. The mass is in the extremum of the left side, so that the spring is completely compressed. Now this spring will execute a restoring force such that it will pull this mass to reach the equilibrium. So now the restoring force is towards the right direction, and the mass is moving towards the left direction. Okay. So that's the reason why it is called a simple harmonic motion, where the force is directly proportional to the position of the object. Okay. So this force is called the restoring force, and according to Hooke's law, that restoring force is always proportional to the displacement of the spring. Displacement of the spring. So the restoring force is given by F is equals to minus K into X. X is the position of this object. F is the force. Is simply the function of the position. And K is the spring constant, which is a constant. And minus indicates, the negative sign indicates that the very essential point that the restoring force and the displacements are opposite in nature. So few basic characteristics of simple harmonic motion. We have this magnitude of the oscillation is the magnitude of the initial displacement, which is also the maximum displacement, is called the amplitude A of the oscillation. The basic characteristics of simple harmonic motion is the time taken for one complete cycle of oscillation is known as time period. Okay, time taken for one full oscillation is called time period T. The frequency is the number of complete oscillations executed per second and is the inverse of time period. So the frequency is mu is the inverse of the time period T. Once we know what is T, you take the inverse of it, that gives you the frequency. The angular frequency is denoted by omega, that's equal to 2 pi times the linear frequency. So these are few characteristics of the simple harmonic motion. And then the next discussion, I will discuss elaborately about how one can construct the equation of motion of a simple harmonic oscillator using the Newton's second. Okay. Thank you.